We are very happy to have Vladimir Rosenhaus here to talk to us about integrability and renormalization under the TBar deformation.
Thank you. So, to start off, as I go along, it will be clear what the talk is about. So, one thing I can start off by saying is that most quantum field theories are not solvable. And by solvable, I mean being able to compute the S-matrix at finite coupling. So the textbook quantum field theory, lambda phi to the fourth, there you can compute the S-matrix in the first order, and lambda in the second order, and then it gets progressively harder, and then one stops. However, there exists some special field theories that are solvable, in which one can either draw all Feynman diagrams to all orders in the coupling and then sum them, or do some other trick by which one can produce the S-matrix at finite coupling. And so there's a large class of theories that are in this category, large N theories. This will not be the focus of the talk, but it's good to mention it. So large N theories are those with a large number of degrees of freedom, so a large number of fields, and then simplifications occur, and sometimes they occur enough in order to be able to solve the theory. So the simplest are vector models, the simplest example of a large N theory. So it's like an example of vector model is like the scalar theory you know from textbooks, lambda phi to the fourth, but now with N fields. So the Lagrangian is of this form. It has symmetry, and this theory is very easy to solve at large N, when the number of fields is large. I won't discuss how it solves it, but it's easy to solve. It's in the solvable category. Then there are also matrix models. In a matrix model now, here we took fields that are vectors. Now we can take fields that are matrices. One can, for instance, work if we work in 0 + 1 dimensions, then we can take a Lagrangian that's trace m dot squared. So m is an n by n matrix plus some term trace m squared plus g trace m to the fourth. So m is an n by n matrix. Indeed, if n was 1, then it would be unclear how to solve this. Well, one thing to say is that this model is solvable. One can solve this theory. It's not obvious from looking at this how one can solve it, but it's not solved by summing Feynman diagrams, but it's solvable. So this is an example of a matrix model that is solvable, but there are other matrix models that are not solvable. So QCD would also be a matrix model because the gauge fields are matrices, the colors, and that is not solvable also now. On the other hand, n equals 4 super Yang-Mills. That is like QCD. It's 4-dimensional, but it is solvable. But it's hard to solve. And then finally on this list, there are also tensor models / the SYK model, which maybe you've heard about, maybe not. And it also is solvable. So one thing to notice from this list that it's not obvious which models are solvable and which are not solvable. Like looking at these Lagrangians, unless we already know how it's solvable. From looking at the Lagrangian, you can't tell if it will or will not be solvable. The solvability usually revolves around finding some trick by which to solve it.
Is there not a more rigorous definition of solvability rather than saying, well, you have to find a trick to solve it?
The definition of solvability I'm using is that you can compute the S matrix.
It's annual order?
Yeah, the finite coupling. Yeah, solvability I'm not doing, yeah.
How do you decide such a thing? I mean, you know, being able to solve an equation or not, it's not a mathematical basis for solvability, is it? I thought you might be talking about infinite linear conservation laws or something.
No, that I'll talk about next in a minute. And indeed, perhaps the reason it's hard to determine if a model is solvable or not is because is because we haven't, as you say, formulated solvability as some precise statement. So we're just using solvability that we can just write down the answer, and indeed, even if it is solvable, it's not clear at which stage do we have the best answer. Like one can get an integral equation as the solution, like in the TOF model, 2D QCD, and that is the solution. Then you can't solve the integral equation, but that's the best.
So to pursue this just a bit more, in X Fourier neutrals, you said that it's soluble, but we don't know how to solve it. You said, or we haven't solved
No,
it.
it's just hard to. So it's partially been solved. So the 2-point function has been computed, but higher point functions have not been computed. But it's believed that they are computable. And there's a long-standing question of how to see from the Lagrangian. Well, n equals 4 is special because there is integrability, there is an infinite dimensional symmetry, but it appears much later in the problem. It's not present in any way that's known from the Lagrangian in 4 dimensions. And so it's a major open problem to understand precisely this question, why n equals 4 turns out to be solved. And so part of what motivated me was that the SYQ model, which appeared a few years ago, was a new class of theories that was solvable, which was different from existing theories. And a question that arose is, how does one generalize SYK? Or what class of theories is it part of that we haven't found yet? So that also is not what I'll talk about. But what I'll do is, in this talk, is take a step back to cases where solvability is well defined. I guess I'm going to erase the board. And so I'll turn to two-dimensional integrable field theories. And I'll say in a moment what I mean. 2 dimensions, they're just 2 dimensions, and by integrable, I'll say in a moment what that means. And so these are solvable. They were largely solved in the 70s and 80s. So to explain how they're solvable, so they're solvable by the S-matrix bootstrap. So let me explain that. So in textbook field theory, we start with the Lagrangian, and then we compute the S-matrix. And that's what we were discussing just previously with the large N theories. We were starting with some Lagrangian, and then we were saying sometimes there's some trick by which we can compute the S-matrix. So while there's in the coupling, in the S-matrix bootstrap approach, one doesn't start with the Lagrangian. One starts with general constraints. So these are general constraints that any consistent field theory or any class of field theories has to satisfy. So these constraints will be like unitarity, crossing symmetry, and so on. And then one just looks for solutions of these constraints. So one just says, if it's a consistent quantum field theory, then the S matrix has to obey these properties. Let's just find all S matrices. And so one directly gets from these constraints to the S matrix. And a question that arises is, once one has the S matrix, what theory is this a solution of? So what's the Lagrangian for this theory that one has written all these solutions? Indeed, it's not obvious that one can certainly impose constraints that one knows must be satisfied, like unitarity and crossing, but it's not obvious that one has imposed. These are clearly necessary constraints, but it's not obvious that they're sufficient. And so one may have what one thinks are consistent S matrices, but then be challenged to find a theory that this is actually an S matrix. So this will be. So this question is the one we will address in the talk in the context of particular two-dimensional, in the context of some specific new two-dimensional integrable quantum field theories, which are found by TBar deformations, which is something I'll explain. Any questions?
When you say what theory, if any, is it a solution of? By theory, you mean here a Lagrangian theory, you mean? Or,
I think that's what I mean.
what about situations where people happily will say, well, maybe not happily, but they will say that there's no Lagrangian relation anyway.
Yeah.
In such, for such cases, this question is not valid question, right?
That's why I said maybe. In that case, I could still. One could still ask them, given an S matrix, one could still ask the question, demonstrate that this is an S matrix of an actual theory. So in that case, instead of writing down Lagrangian, I would ask them to write down all correlation functions, because that's an observable that in principle follows from the S matrix, but in practice is hard to obtain. And yeah, even at the level of the Lagrangian, if one has a confining theory, then you could ask, do I mean the fundamental Lagrangian, which is not useful for computations, or some effective Lagrangian? And I guess I would say that I would like to know both. I guess on a related point, the discussions of theories that don't have Lagrangians, I'm not sure I understand what that means, because a theory needs to be something that an experimentalist can put in the lab and create that theory, and you need a Hamiltonian to build the theory in the lab. So
aren't S matrix elements sufficient to do physics if you can compute the S matrix?
If we want, suppose we want to study theories that don't naturally appear in nature, like the standard model naturally appears. if we write down a Hamiltonian, then someone can go into a lab and just create that Hamiltonian, create interactions which imitate that Hamiltonian, then we can test it with the correct test method. If we don't have a Hamiltonian to give the experimentalist to create, then how do we ever get this theory? All right, so I was planning two parts to the talk. The first will be a review of integrability, by which I really mean integrability in the context of 2D QFTs. And in particular, I'll focus on the cinch-Gordon model, which is the simplest integrable theory. And then I'll discuss TBar. So in particular, so these TBar theories were defined by Smirnov and Zamolodchikov by what I'll call a TBar flow equation. So they defined the theories in a particular way, which I'll describe, and from this one can get the S-matrix. It's not difficult to show that their definition, one can equivalently map to a definition of how the S-matrix changes under this deformation. So we'll take that as a starting point, and the question we'll want to ask is, what is the Lagrangian for these theories, these TBar deformed theories? And we'll provide a small part of the answer to this in a specific context.
For completeness, I
Yes.
give you the equations of motion, but no Lagrangian. How about that situation? Is that satisfactory enough for
Now you're thinking of a Silev theory?
well, there are others too, I think. He's not the only one.
I don't know.
Okay.
So everything I'm saying here is contained in this paper. The paper by the Zamolodchikovs from '79. Really a remarkable paper. So we're going to, so let me introduce notation. So we're going to be computing S-matrices, and we'll label the particles by their rapidity theta. So I index the particles by the index I, and then their energy is cosh theta, and their momentum is sinh theta. So this is the definition of the rapidity theta. And the S-matrix, the 2 to 2 S-matrix, will only depend on the difference in rapidities between the two particles, so I'll just call that theta. So we'll be computing the 2 to 2 S-matrix. And the S-matrix will only be a function of theta, the rapidity difference between the particles.
P is the momentum.
P is the momentum, E is the energy. And when 1 plus 1 dimensions, so there's only one direction. These are just more convenient variables than. So in fact, to connect with variables that you know, so let me call this P1. So let me state the following. The incoming momenta we'll call P1 and P2, and because we're in 1 plus 1 dimensions, the outgoing momenta have to be the same. They're again P1 and P2. Because if you impose energy and momentum conservation, you get that the outgoing momenta are the same as the ingoing. All the particles can do is swap momenta if they like. This is easy to check. So that's why, good. The Mandelstam variables, P1 plus S is P1 plus P2 squared, which is just 2m squared 1 plus cos theta. So I just plugged in P1 and P2 into here, and you get this. Yeah, because if you just expand this, P1 squared is m squared, P2 squared is m squared, that gives 2m squared, and then 2P1 dot P2 gives the cos theta. The Mandelstam variable T is P1 minus P2 squared, because in usual notation, P3 is P1. And this is just 4m squared minus S. And the Mandelstam variable U is just 0. Yes?
Are you going to focus on the 4-point amplitudes?
Good. Yes. I'll explain why. Good. So this part is clear? These are just, so all the Mandelstam variables in 2 dimensions, they simplify. There's only one independent Mandelstam variable, S, and T is just 4m squared minus S. And we'll write everything in terms of theta because there's only one. The S matrix depends only on one variable theta. And the thing we're going to do, so integrability here will mean in the statement that there is no particle production. In other words, one assumes that the 2 to n S matrix is 0 for all n that are not equal to 2. One can show that this statement of no particle production is equivalent to the statement of having an infinite number of conserved quantities. But this one is easier to understand. So this is what we're going to do. We're going to try to find integrable theories, ones that don't have particle production, and see what we get. So now, we impose constraints that we know a field theory must satisfy. So the first constraint is unitarity. That the magnitude of the S matrix squared is equal to 1. Now, normally, so in quantum mechanics, this is familiar, because in quantum mechanics there's no particle production. In quantum field theory, you would have normally written S of theta squared is less than or equal to 1, because normally you have particle production, and so if you're sending 2 particles in, you can get 2 out, but you can also get n out, and so the 2 to 2 S matrix, that square just needs to be less than or equal to 1, because the remainder is compensated by 2 to n. But in our case, we have said there's only 2 to 2, 2 to n is 0, so that's why we're imposing that it's equal to 1. And it's already clear why this will impose, by imposing integrability, no particle production, we now have an equality instead of an inequality, so there's hope that we can solve it. And the second condition is crossing, which is the statement that you can look at the Feynman diagram, you can have time run from bottom to top or from left to right. In other words, you can expand in the S channel or in the T channel. So in this language, S of theta is S of I pi minus theta. The reason I pi minus theta is because you can tell that sending theta to I pi minus theta, it interchanges S and T. You can see this because cosh of I pi minus theta is minus cosh theta. So if you plug in theta goes to I pi minus theta, you get from S to T. So these are the two constraints. And what the Zamolodchikovs did, actually in this context with one species, I think it was done earlier, was they just said, we need to solve this equation and this equation, so what's the solution for S that solves these equations? So we haven't said what the theory is yet, we just wrote down constraints, and now we want the solution. I'm going to use this part of the board. Since when I say next, anyone can just look up online. So now one thing to notice is that sinh of I pi minus theta is equal to sinh of theta. So a solution to these equations is S of theta is sinh theta minus I sine alpha over sinh theta plus I sine alpha, where alpha is anything. You can see that this is a solution because it satisfies crossing by this property of sinh theta. And you can easily check that it's unitary, that S of theta magnitude squared is 1. So that's a solution. So this is known as the CDD factor. This. In fact, as is sort of obvious, if you take any product of these CDD factors with different alphas, that's also a solution of these equations because each term individually satisfies both of them, and so the product also does as well. And so now we can ask, and should ask this question that we said at the beginning. So we have the solution, but what theory is this the solution of? So is the setup clear so far? So we focused on two-dimensional field theories. Then we restricted to those that were integrable, which we defined as having no particle production. And this reduced the constraint of unitarity to this equality. So we imposed unitarity crossing and then looked for all solutions. And what we got is this, or product of these. And now we want to ask our question of what the Lagrangian is, what Lagrangian gives this S matrix. And the theory that gives this S matrix is the Sinh-Gordon model.
So when you didn't put an amplitude in front of sine alpha?
Yes?
So you can put any function instead of sine alpha, yes?
You say, why did I put sine alpha as opposed to any function of alpha?
Any function of, you can have 1 and 2 together.
Yeah, you can, I mean, alpha was a made-up thing, so, yeah.
Yeah, but I mean, sine alpha has absolute value of 1. I mean, less than
Okay.
1. But
This is a question I was thinking. To check unitarity, so let's see, if we check unitarity, so if I compute S squared, then I have sinh theta minus I sine alpha over sinh theta plus I sine alpha sinh theta plus I sine alpha sinh minus I sine alpha. So here I assume alpha is real, and then they cancel. So indeed, all I needed here was any real thing. Yes. Yes, that's correct. Good. The reason I put, I mean, alpha is just what I wrote is general because alpha is just a made-up thing.
yes, but you basically constrain yourself to the absolute value list.
I see what you mean. But I didn't say alpha. I was going to say I will allow you to take complex alpha,
Yeah.
but I need sine alpha to be real.
And they still cancel.
Hmm?
They'll still cancel if Alex.
No, because when I took the Hermitian conjugate, I assumed sine alpha is real.
But I think it'll still work. It's just like, it's not the numerator cancels, it's just the things upstairs are the same as the things downstairs. You get one, but it's other one.
Okay, anyway,
Yeah.
yeah. Oh, we were over here. Right, so the Lagrangian that corresponds to this S-matrix is the Sinch-Gordon model, where one identifies, so here I put in the B, one identifies alpha with pi b squared over 8 pi of b squared. And if one takes this Lagrangian, so think of cos b phi minus 1, just Taylor extend this in B, so it's phi squared plus phi to the fourth plus phi to the sixth and so on. So it's just a bunch of terms, and if one starts computing the S matrix with this Lagrangian, so something that one can do is compute perturbatively in B. The S matrix S of theta with this Lagrangian. So just start computing, just draw the Fermi diagrams and so on, and then you'll see that that matches the perturbative expansion in B or alpha of what I said the answer is. So that's a way to check to a few orders that this Lagrangian is what goes with that S matrix. So this is easy to do with one loop, and then it gets harder. This was done by Aryapov and Kropin in the 70s. Nevertheless, you could still ask, what's a better way of understanding why that S matrix goes with this Lagrangian. Because checking is, you could ask how people knew that it was this Lagrangian that goes with that S matrix. And an answer that one can give is that, in fact, the Sinch-Gordon model is the unique integrable theory of a single scalar with no derivative interactions. So to get the S matrix, we imposed integrability at this level, and then we found the solutions, and we got the S matrix. At the level of the Lagrangian, you could ask, how do we impose integrability at the level of the Lagrangian? So one thing you could do is you could construct the Sinch-Gordon Lagrangian. So start with d phi squared plus phi squared, and then put something here, lambda phi to the fourth. And then compute the 2 to 4 S matrix. And you'll see that it's not 0. And so you say that's not good. We want a theory with no particle production. So then we add an appropriate number times phi to the 6th in order to make the 2 to 4 S matrix 0. Then we compute the 2 to 6 S matrix. We find something non-zero. We add something with phi to the 8th and keep going. And if we do this procedure and then resum everything, you'll see that what goes there is Cauchy. This procedure is also tedious, though conceptually pleasing. Another thing one can do is one can ask. So we know that the stress tensor is conserved. That's always true, and the stress tensor is just d phi squared. The other stuff doesn't matter. One could try to impose that there's a higher spin conserved current. So alternative to this, so to look for an integrable Lagrangian, one imagines that one has a higher spin conserved current of the form d phi to the fourth plus some number d squared phi squared squared. So this by dimensional analysis, this is if we have a spin 4 conserved current, this is the form it must take.
Yes, could you please repeat why does it imply integrability?
No particle production?
I mean this higher spin current, or what is it called?
So I'm going in between two definitions of integrability. Now I say by integrability I mean having higher spin conserved currents. So I'll declare the theory is integrable if the system only had a finite number of degrees of freedom, we say it's integrable if you have as many conserved quantities as the number of degrees of freedom. If it's a field, like the classical mechanics. In field theory, we say it's a little more tricky because an infinite number of degrees of freedom, but then we say you need to produce an infinite number of conserved currents. If you have the conserved current, then you can get the conserved charge. So that's what I was looking for. I was looking for some conserved current that's not the stress tensor. And so I looked for one that's dimension 4, or spin 4, it only has,
And you will construct infinite array.
That's right. In fact, just imposing that I have a spin 4 conserved current of this type will then, so I take a scalar field theory with some general potential. I say I want this theory to have this with any number here as a conserved current. So I compute the equations of motion for my theory, and then demand that this be a conserved current, and then this constrains the potential. And the only solution is caution, or cinch. So that's an alternative way. So in this, yes, I should speed up. So in this way we have, so I think I've demonstrated in some detail that in the case of these two-dimensional simple integrable theories, we know both the S-matrix and the theory. That we impose the constraint of integrability of no particle production. This gives us the solutions to the S-matrix bootstrap, and it also tells us the Lagrangians. A question you could have asked is if this Lagrangian is the bare Lagrangian or the renormalized Lagrangian. Because it's standard in field theory that if you write down Lagrangian and then start computing, there'll be UV divergences and you have to have counter terms and so on. And so one could ask again here, what I mean by this Lagrangian, if it's the bare one or the renormalized one. And that's a legitimate question. But in fact, in 2 dimensions, the answer is that, in short, is that they're the same. So the bare Lagrangian and the renormalized Lagrangian are the same because the only divergences, the only UV divergences that occur are tadpole diagrams. So diagrams like this. And so on. It's only these diagrams that produce UV divergences. Other diagrams like this are UV finite. In 4 dimensions, this is in the standard field theory used. In 4 dimensions, this is divergent. In 2 dimensions, it's finite. So the only divergences are of this tadpole type. And so we can add a counter term, a mass counter term to cancel this diagram. Delta m squared phi squared, with delta m squared as this loop. And then sum all these counter terms, and that will sum to a counter term Lagrangian that's precisely of the same form as the bare Lagrangian. It so happens that if you compute all these diagrams, they all sum into a cosh. And so renormalization just consists of shifting the mass. Just consists of shifting the mass. So renormalization is extremely simple in two-dimensional theories without derivative interactions. And so that's why I got by giving a classical Lagrangian. And at the same time writing down the full quantum S-matrix. All right, now I'm going to move on to part 2, to TBar. Are there any questions about this?
So when you constructed the S-matrix to find the unitarity and crossing constraints on that, you said that you are just looking at the 2 going to 2 process.
Yes.
But now when you write the Lagrangian, you have all sorts of terms, so that will give rise to S-matrices which are not just 2 to 2.
Like which ones?
I mean, if you just expand the potential, will that not give you S-matrices which are not just 2 going to 2?
Good. So 2 to n, I'll get 0 by construction. So to get this Lagrangian, I demanded that 2 to n be 0. That was that's how I got these terms. That was one of my constructions for getting this Lagrangian, was saying that 2 to n should be 0. Because remember, I said let's start with phi squared plus phi to the 4th, and then compute 2 to 4, we'll get something non-zero. I add phi to the 6th with the correct coefficient, make it 0, and so on. So we construct the Lagrangian so 2 to n is non-zero. You might ask, okay, what about 3 to 3? And in fact, 3 to 3 is not 0, and there's just a product of 3 2 to 2 S matrices. So that's something I didn't discuss. So n to n is non-zero, but it's just a product of 2 to 2 S matrices. Roughly, the picture is like this. So 3 in, 3 out, and the 3 to 3 S matrix, you just take a product of 3 2 to 2 S matrices. This one, and that one. All right, let me now turn to TBar. So TBar was defined by Smirnov and Zamolodchikov, and the statement is the following: take any field theory, and they're going to define a one-parameter family of theories. And the definition is going to be that they need to satisfy this equation. So the lambda is the deformation parameter. So T means I guess I should say this. So there are 2 coordinates. So we're in 2 dimensions. So there are 2 coordinates x and y, and we, instead of working with x and y, we work with z and z bar, where z is x plus iy, and z bar is x minus iy, and then the components of the stress tensor. The stress tensor has 2 components, and then we call tzz as just. Well, it's actually not do that. So this is some particular. So the deformation is TCC, T z bar minus T z bar squared. So it involves all the 3 components of the stress tensor. So one does this particular deformation. So this is why this is called TBar, because this term is TBar. The actual quantity on the right-hand side is the determinant of the stress tensor. That would have been a better definition, but it's too late. So this is what's known as the TBar flow equation. So L of lambda equals 0 is the original theory. And one should note that the stress tensor that appears on the right is the stress tensor for the theory at finite coupling lambda. So one starts, the procedure is the following: you take any theory that you have, and then the goal is to find a broader class of theories which have an additional parameter lambda, and these theories satisfy this equation, and at lambda equals 0 is your original theory. So that's the definition. It's important to note that this is not an RG equation. There is significant confusion about this. TBar is not RG flow. It's just a deformation of theories. All quantities that appear in this equation are renormalized in UV finite. So this is a fully quantum equation. The left-hand side is the renormalized Lagrangian. The right-hand side is an operator that was defined by involves the renormalized stress tensor, and the operator on the right is defined by a point splitting procedure, which I want to discuss. So everything is renormalized in UV finite. This is just a deformation of theories. And because of that statement, from this definition of these theories, it's not obvious. So it's not, given some starting Lagrangian, it's not obvious how to solve this equation, nor is it obvious how to get the actual Lagrangian. So as a warm-up, which is useful, is to take the classical version of this equation. So I'll say in a minute why this is viewed as interesting. But for the moment, let me just take an example where we take the classical version. This will be useful anyway because classical is tree level. So we let L of lambda equals 0 just be a scalar field theory with some potential, any potential, and then we solve that equation. The answer, which was found by Benelli and collaborators, and for a special case it was found by Tateo and collaborators, is the following. So this is just some Lagrangian, so it involves the square root 1 plus 8 lambda bar d phi d bar phi, where lambda bar is defined in terms of lambda and the potential V. So it's easy to check that this is a solution. Take this Lagrangian computed stress tensor, and then you'll see that if you take dl d lambda, that equals the determinant of the stress tensor, which is the right-hand side. And so it satisfies that equation, and at lambda equals 0, one recovers the original Lagrangian. That won't happen because at lambda equals 0, we can expand. So Taylor expand this to first order. The 1 cancels the 1. The lambda bar cancels lambda bar, and we're left with d phi d bar phi, which is the kinetic term, and then here we have b.
So lambda is a real constant,
Lambda is a real.
whereas lambda bar is a function, complicated function.
Yeah, this shouldn't have been called lambda bar. This is just shorthand.
I see.
I didn't. Yeah, it's just shorthand.
Why is this a tree-level result?
Because I took a classical Lagrangian, and I turn this into a classical equation.
Oh, I see.
Whereas for Smirnov and Zamolodchikov, this is a fully quantum equation with renormalized quantities. Indeed, so now we get to why these theories are viewed as interesting. So one knows. So if we put the theory in a circle, so right now we're discussing 1 + 1 dimensions, but we can put it spatially in a circle, and then talk about the energy levels. And in particular for these theories, from this equation defining the theories, one can derive how the energy levels are changed as a function of lambda. And from this equation, one can derive how the S-matrix depends on lambda. And so this is why TBar is called a solvable deformation. So the original theory that you start with is not necessarily integrable, though it's convenient to take an integrable one. But the point is that one can do this deformation and construct this much richer class of theories. So even starting with a scalar, one gets this much more complicated Lagrangian, and one knows as much information about this theory as one did about the original one. So one has differential equations for how the S-matrix changes with lambda and how the energy levels change with lambda.
I assume the S-matrix is some differential equation for the S-matrix. How complicated is it?
Good. In fact, the equation for the S-matrix is simple. So S lambda of theta is S of theta. So lambda equals 0. The S-matrix of the original theory times e to the I lambda m squared sinh theta. That's it. So the S-matrix is remarkably simple. Even supposing we start with just a free massless. Indeed, this is a good case if you take V to be 0. So you start with a free massless scalar. The classical TBar deformed Lagrangian is square root 1 + 8 lambda d phi TBar phi, which is the Nambu-Goto action. So classically it looks like a complicated action, and the S-matrix is just this exponential. So one has what appears to be a complicated Lagrangian and a very simple S-matrix. And indeed, this was the TBar deformation of a free scalar. The TBar deformation of a different theory will be more complicated, and yet one continues to have this very simple change in the S-matrix. And this, so Smirnov and Zamolodchikov showed this for, well, anyway. They demonstrated that this is the change in the S-matrix that follows from their equation for integrable theories, and Dubovsky and collaborators wrote down a form for non-integrable theories very similar to this, conjectured it, and then proved it in some sense. We gave a simple derivation that this is true. So it's very simple to see from that equation. All right, good. So having said all of that, now I want to return to the question we posed at the beginning. And the question was, so we had this chart, we have the TBar flow equation. That's that equation over there on the left. We have the change in the S-matrix. That's this. And the question we want to ask is, what is the Lagrangian? What is the Lagrangian that corresponds to this S-matrix? Now, you might say that I already told you the Lagrangian, for instance, this one for the TBar deformation of this theory. But as I emphasized, this is a classical Lagrangian. It's not the quantum Lagrangian. And if you compute and start computing with this Lagrangian, for instance, the S-matrix, you'll get UV divergences. And so you'll have to renormalize it. And so the question still stands of what Lagrangian gives this S-matrix.
So in the mass case scenario that you discussed, that your S-matrix would be the same, it doesn't depend on lambda here? If mass equals to 0, then...
If you're asking about the case where we send the mass to 0.
Yeah, so it doesn't...
Good. So if we send the mass to 0, the rapidity, so when we send m to 0, we at the same time send theta to infinity. Because you want the energies of the particles to be finite. And the energy was m cos theta, and the momentum was m sinh theta. So as you send mass to theta, you send theta to infinity, so that this quantity remains finite. And in this limit, sinh theta goes to cos theta. And so it's in the massless case, it's better to just replace this with the Mandelstam variable s. So then the S matrix is usually written as e to the I lambda s. And that is the S matrix for the Nambu-Goto theory. The statement, what I said is confusing because, well, let me not discuss that. Good, so let me just, in words, say how one carries out this procedure of getting the Lagrangian, and then I guess I'll stop. So again, to summarize, Smirnov and Zamolodchikov and others defined this nice new class of solvable theories. Or even forgetting that, we have these theories where we have this simple S matrix, this exponential. And the question we want to ask is what Lagrangian corresponds to these theories. And the question in our case is much richer than it was for the Sinh-Gordon model, because for the Sinh-Gordon model, we said that the renormalized Lagrangian is the same as the bare Lagrangian, and that was very special because Sinh-Gordon didn't have any derivative interactions. Here we do have derivative interactions, which you can see from expanding the square root, and so we do get UV divergences, and we have to renormalize, so the question is much richer. So the approach we take to get the Lagrangian is we start with the classical Lagrangian, that's correct at tree level, and we then start computing the S matrix. So we compute the two S matrix, the one loop, two loop, and so on. In this process, we'll find UV divergences. We do the standard procedure in field theory. We add counter terms to cancel the divergences. Now, all of these theories are non-renormalizable in the field theory sense. The coupling lambda has negative dimension. And so we expect that we need to add an infinite number of counter terms. So that's what we expect. As a standard in field theory, the finite part of counter terms is ambiguous. And we usually fix those experimentally. Like normally, like the textbook QFT one says that we impose that the amplitude for S equals 4m squared be given by this, and that's how we fix the finite part of counter terms. And this is why in a non-renormalizable Lagrangian, where we have an infinite number of counter terms, we have to fix an infinite number of coefficients, and that's why non-renormalizable theories are not useful for UV physics, because you need an infinite number of data to predict anything. In our case, we fix all of the finite parts of the counter terms by demanding that we get the S matrix that we want, this S matrix. And we hope that condition is satisfiable and will give a unique Lagrangian. It's not obvious that either of these.
Questions. Quick questions. If you have non-normalizability, how can you still expect a well-defined S matrix like this?
Good. We just take the Lagrangian, and we perturbatively in lambda start computing the S matrix. And then we perturbatively in lambda start renormalizing and fixing the finite part of counter terms to get this S matrix. That's all. Everything is done in perturbation theory in lambda.
But in a non-renormalizable theory, is there a complication? I can't put my finger on it, but
no, normally we don't consider non-renormalizable theories for the reason I said that they're not predictive in the UV. So we only
but
consider.
it's what you have, you said.
Good. But I'm doing something different. I'm fixing the finite part of counter terms to get the S matrix that I want.
Can we not think of this as effective field theory? Because
No, we're not really doing effective field theory.
Either.
We're,
Okay.
I mean, we are in the paper because we only went to, so in the paper we just take the TBar deformation of a free massive scalar, so we take v of phi is m squared phi squared, and then we carried this out to second order and obtained the renormalized Lagrangian, which I won't write down. One qualitative point is that the renormalized Lagrangian, there are now multiple terms with different couplings. For instance, in the bare Lagrangian, there was only one coupling lambda. And so in the bare Lagrangian, one has terms like phi to the fourth, and d phi, d bar phi to the fourth, and so on. And they all come with the same coupling lambda, or lambda divided by 4. But once you renormalize, these couplings become different, so they become independent. So the renormalized Lagrangian is more involved than the bare one, significantly. That's one qualitative point.
It's
So
not
yes.
just like for normalization.
It's really no, because it's
you have all sorts of higher derivative terms.
That's right, because the Lagrangian we start with, is
I guess it's just m squared, right?
d phi, d bar phi. No, because we take the TBar deformed theory. So we take this Lagrangian and then do RG on that. So we renormalize. So we start with phi and d bar phi. Well, let me just write this down. So if we just look at tree level, G is equal to H is equal to lambda. So the Lagrangian is just has a lambda sitting here and the lambda sitting here. So if you just take V is m squared phi squared and plug into this and Taylor expand, you'll get this. The first few terms will just be this with G equal to H equal to lambda. Then we take that Lagrangian and then renormalize to compute the S matrix and renormalize to one loop, and we get some divergences, and so we correct we write down the renormalized couplings, and what we get is something of order lambda squared for G, and then a log m squared over lambda UV squared, the UV cutoff. And similarly for H, and you can see that the coefficients in front of the log are different. So we now have two different couplings. An interesting question for the future is to understand what happens at higher orders in lambda, because again we have a very simple S matrix, just this exponential, and one might think that should correspond to a simple Lagrangian, or maybe not. Clearly the Lagrangian will be complicated. Already the classical Lagrangian was non-trivial, and the quantum one is much worse, but perhaps there's some way of writing it in which it appears simple, or maybe not. the second is to repeat. So we did the calculation for the TBar deformation of an integrable theory, just a free massive scalar. If one does the TBar deformation of a non-integrable theory, the procedure is, one can do the same procedure, but it's more involved because it's not sufficient anymore to look at the 2 to 2 S-matrix. One now needs to look at 2 to 3, 2 to 4, and so on. And now it's less clear that you have enough degrees of freedom in the counter terms to get the S-matrix that you want. Finally, at least for me, the broad motivation for this was to find a way to go beyond integrable theories. For integrable theories, there are these very set rules, and they were solved in the 70s and 80s. Yet we know, as we discussed in the beginning, for large N theories, there are things like the SYK model which are not integrable. They don't have any conserved quantities, non-trivial conserved quantities. They exhibit chaos, and so in many ways they're much more interesting. And so it would be good to find some framework to encompass non-integrable theories, but that still have some class of non-integrable theories to go beyond it. All right, thank you.
If I remember correctly, in the